All right, so what we're looking at here is our two uh, bivariate, I almost said two variate, bivariate graph looking at these two categorical variables with the explanatory variables, the eyewear, and the responses, the asthma. So we've already done this, and when we did this, we're like looking at the proportion of the folks who don't wear eyeglasses or contacts at all, who have asthma, and the proportion of people who wear eyeglasses who have asthma. And it looks like there's a little bit of a difference in these proportions. If there was an association between these variables, we would expect a difference. And if there's no association at all, we would expect all these bars to be straight across. But as all hypothesis tests are for, is we already know that there's a little bit of a difference in the sample, but we're going to test whether that difference is significant, whether we think that we have enough evidence to suggest that the population difference is these proportions are different in the population, that these differences are significantly far apart. Or these proportions are significantly far apart. The differences are big enough. All right, so it's going to be a long slog. We've got a lot to do, but let me scroll down to where we're starting to do it. So the first thing we're going to do in the beginning of the semester, we looked at these two-way tables, and so we're going to start by doing that in Python. And the code is crosstab, and it's a pandas function, so pd.crosstab. And then I'm putting my explanatory variable first, my response variable second, and I'm getting the marginal counts as well. So the totals in here. Without this, let me do it without it first, and then I'll put it in. So let me cut that out. So what this is saying is there are 798 people who wore both eyeglasses and contacts, and at the same time did not have asthma. 158 people who both wore contacts and glasses, but did have asthma, was diagnosed with asthma, etc. So these are just the counts in each of these when the person has both going on at the same time. If I'm able to see the margins, then these will be totaled up. And what that helps us to do is to see, well, it's 798 out of 956 who don't have asthma amongst these folks who both wear contacts and eyeglasses, and only 158 out of this 956 who do have asthma. If there is no association between these variables, then these proportions, the 798 divided by 956, should be the same, or more importantly, I guess the yeses over the totals. The 158 over the 956 would be the same as the 48 over the 308, which would be the same as the 18.5 over 1129. And all of these individual what's going on for asthma within these individual categories would all be the same, even if you looked at the whole thing altogether. So 789 over 5,112 would be the same proportion. And so these are hard to tell, the proportions here. We sort of looked at it in this graph up here. This is calculating the proportion in each of these categories, but it's certainly hard to tell with just the counts. And so what we're able to do, is with normalize, and I'm going to go by row so that it actually gets the percentages like I was describing them within each of these categories. It's going to calculate the percentage of yes asthma and the percentage of no asthma for the both. Percentage of yes asthma for contact lenses and the percentage of no asthma for the contact lenses, etc. It's going to go up and down and do all those percentages. And there they are. So I rounded to 3 decimal places. If I don't have that, and I can't have the dot then if I don't have that. If I don't have that, then it's just got a whole bunch of decimal points, and those kind of just make it harder to look at. So like that. And if I don't have the times 100, then it's writing it as a decimal, which is also harder to look at. So, that's certainly what is being graphed. It's the actual decimal value, what we would call the proportion rather than percentage. But I think for our eyeballs, looking at it in percentage form is a little bit easier. So these percentages look pretty similar. I mean, here's 16.5 versus 14.7. Okay, those are different. If there was no association at all in this sample, then they would all be equal to this 84.6 and this 15.4. And there is a little bit of difference between these different categories. So both is different from contact lenses, is different from eyeglasses, is different from neither. But is it different enough to think that the population that this data came from has a difference? Well, that's what we're going to investigate. So the first slide and you can see there's lots of slides, but the first slide is laying out the null hypothesis and the alternative hypothesis. And the null hypothesis is basically we're assuming there's no association in the population, and then looking at what's going on in the sample and seeing if there's enough evidence to support that, that's probably not true. We wouldn't get a sample that's has this much difference in those proportions if it was all equal in the population, and so you'd have enough evidence to support the association. The way it's talked about in the chi-squared is that your two variables are independent, that they don't depend on each other is another way to think of that. So they're dependent. That's going to be the alternative hypothesis, but the null hypothesis is not. They're independent, nothing to do with each other, no association. Okay. So it's hard to tell. It's still hard to tell. So we're going to look at some visualizations, slightly different way of visualizing it than what we looked at before. So here's what's called a stacked bar graph. And what it does is instead of just having the percentage of yeses, that's what these orange tops are. You can see that from the key here. The percentage of yeses all at their relative heights, so you can see the difference in those heights. It's putting the entire all the people in both together in the proportion of no's, and then on top of that is stacked the proportion of yeses. For contact lenses, the proportion of no's to a certain decimal value, and then the rest up to the 100% is the proportion of yeses. So with this eyeball, and it's basically the same information that we saw here, but here we're almost zoomed in, so we can see those little differences. Looking at this one, it looks like there's virtually no difference, right? So I'm having a little bit less confidence that we're going to have significance. So this graph is very, very similar to a very common way to visualize this stuff called a mosaic plot. And what a mosaic plot does is it not only gives you that, here's the proportion of no's all the way up to then the proportions of yeses stacked on top of that. So for each of these categories, and you can see that this is a little bit lower than that. These are virtually equal, and that this is a little bit higher than that. So thinking of the proportion of yeses, the proportion of yeses is a little bit higher in both in the eyeglass category and a little bit lower in the contact and neither categories. But not just the heights of these bars is giving us information, but the width of these bars is also giving us some information. These are based on how many people in the data set are in this neither category. How many people in the data set are in the eyeglass category? So it's giving that univariate feel at the same time as this bivariate feel. And I call it a mosaic plot because all these little blocks look like mosaic tiles to whoever invented this. So this is a little bit more complex because it's got more information in it, but it's a very common visualization when you're looking at these two variables like this. So finally, without further ado, we're ready for the hypothesis test, and it's called chi-squared. And so what I've done here is labeled one of these contingency tables, one of these two-way tables, without the marginal. I'm just looking at the counts. And so that's going to be printed down here. But it's also used when I run this code. So this is just a print statement, so we're seeing what we're gonna see. The chi-square value, that's the test statistic, the p-value, and that's what we're gonna see if it's less than 0.05, and if it is, we have a significance, and if it's not, then we're gonna say, hey, there's not enough evidence here. And then the expected counts. So I'm gonna run this and then talk a little bit about how this p-value was concocted using these expected counts. And this table is just going to give us the actual counts in the data, what was observed. So the stuff that we were looking up at over here is the observed counts in our sample, and the expected counts are basically going to calculate what would these be if you had 956 people in this both category, and the percentage of no's was exactly what it is for the whole data set. So it's making it so each of these counts, this is what we would expect if the proportions or the percentages are all equal to this, all equal to each other, but they're getting it from the percentage overall. So this would be 84.6%, this would be 15.4%, and these numbers in here, the expected counts that we're going to see, are made up, calculated, so that the percentages would come out right, so that this over the total would be 84.6 rather than what it actually is in the observed data, 83.5. So sorry about that long-winded description, but trying to explain what the heck is going on here. So when I run this, Shazam, it gives us this statistic, which I'll explain a little bit when we get over to the slide. The p-value, and wow, what a big p-value. It's almost 50%. So it's supposed to be less than 0.05 if we have significance. Guess what? We have no significance. This is absolutely not any evidence that there's an association between these two variables. It has nothing to do with each other. At least it looks by this test. And then this table right here, and I'm actually going to just move this so that it lines up a little bit better, the 808 and the 260 and the 954 and the 2299. These are the expected counts that would make those percentages equal to what I would have said with the whole thing. And so printing this table shows what the observed counts are, and they're different, right? Here's what actually happened. Well, and how many yeses in the both category. For the percentage to all come out equal, you'd have to have 808 point blah, 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 and 147 point blah, blah, blah in those slots, right? So they're different, but apparently not different enough. So I'm gonna go over to the slide, and I know this is turning into a monster video. It's by far the record so far. So in the second slide, I put those two two-way tables that we started with. In the third slide, I've got the stacked bar graph. In the fourth slide, I've got the mosaic plot. And in the fifth slide, I've got this output as well as this table. And so the chi-squared test for independence, what it does is it takes these observed counts, subtracts off these corresponding expected counts. That's what this numerator up here, squares that difference so that you never get negatives. It's basically, they have to square it. They could have taken an absolute value, but they didn't. They have to square it so that this always comes out positive, so that when you add them all up, it totals and gets bigger and bigger and bigger the more you add up. Otherwise, the negatives would cancel out with the positives, and you'd get nothing. So they take the observed minus the expected, square that difference, and then divide it by the expected. That kind of normalizes it so that if you have a big difference just because it's big numbers, that it won't contribute so much. But they do that for every cell. So they go 798 minus 808, blah, 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 square that, divided by 808, blah, blah, blah. And then they go 158 minus 147, blah, 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 and square that, and then divide by 147, blah, blah, blah. And sorry, I keep saying blah, 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 but I don't want to say all these decimal numbers. I probably should figure out how to round this so this table comes out rounded, but I don't know how to do that. And then it adds all that up. That's what this big looks like something on a fraternity or a sorority's wall, because it's a capital Greek letter sigma. So it adds up all of those squared differences divided by the expected counts, and it adds them all up. And in this case, it got 2.868, yada yada. Okay, so this statistic, that's the chi-squared statistic. We had a z-score, we had a t-score, we had an f statistic, now we have a chi-square statistic. And this is so small that it easily could have happened just by chance, even with the assumption that in the population, those proportions of people with asthma in each of these categories is identically equal. That's what we're assuming. Even given that, there's a 41% chance that you could have these observed counts as different from that as they are, or even more different than that. There's a 41% chance that could happen. So that's super easy to think that just happened by chance. Certainly, it's not less than the 0.05 for significance. So it's not significant. Okay, that is enough for this marathon slide. I hope you understood some of that, and if not, that you're asking good questions. All right, take care, everybody. Bye-bye.